Hello and welcome back. Today is the last lecture of this week, that is the second week. So, we finished the last lecture by talking about the modes of the laser. Okay. So, we said what is a mode, essentially taking reference from quantum theory of light. We said that okay, this is a possible combination of the polarization, frequency, direction. Now, the question that we raised toward the end of the class was, are all the modes permitted in a laser, in laser cavity? The answer is no, it is not. So, the only modes which are permitted has to satisfy a condition. So, what is the condition? So, the condition to be satisfied is this. Okay. So, what are these? So, we created this cavity, right? So, you have this active medium here. So, you are pumping and then your light is going and bouncing off between these two. The length of this cavity is L. Okay. Lambda is the wavelength of the light. Okay. So, if I can have the information regarding lambda, I can very easily get the information for frequency, because they are related by the speed of light. Okay. And what is this m? This actually give you the particular mode. Okay. So, m can be any integer value, 1, 2, so on. So, I will say that okay, this is the mth mode. Okay. So, what essentially this mode is, this, if I use this same cavity, then this condition actually means that only those modes are permitted that will create standing wave here. This is not very surprising to you, right? You have already seen this in your high school physics, right? So, for creation of standing wave, you have seen earlier using like two fixed surfaces and making a say string or wire tied to both ends, and then just letting it oscillate. There are certain modes that will be actually creating standing mode, and you can figure out what is the particular standing mode and the corresponding frequency or wavelength from this. So, here what does that mean in case of laser? In case of laser, it will mean that all these modes that will actually form standing wave will have their nodes at the turning points, that is at the mirrors, two end mirrors. These mirrors, as we have already said, are called end mirrors. Okay. So, what is a node? So, I said this, for creation of standing waves there should be nodes at the mirrors, or actually to be precise at the end mirrors. What is node? A node is a point where the amplitude of oscillation is 0. So, this refers to 0 amplitude oscillation. I hope you know this. I hope that I am not, you are not hearing it for the first time. Now, we are just redefining things in the present context. Okay, that is what I expect. So, you have to have nodes here. So, what is the maximum wavelength that you can have, so that can be counted as a mode, meaning that will create a standard standing wave, that is just this one, right? Half wavelength here, after reflection fills up another one. So, here essentially m equals to 1, lambda equals to 12, very easy to figure out. You can have like this. So, you keep on increasing the m, 2, 3, 4, you go to n number. So, there will be still nodes here and also inside, but my primary requirement is that there should be nodes at the ends, end mirrors. So, why is this requirement? Okay, from where it comes? See, I would like to have my laser to have a large intensity, right? So, I would want that since all the stimulated photons are in phase to start with, all right. So, now until unless I have this condition, after back and forth movement, if they are random, they will interfere destructively, and I do not want to have any destructive interference. So, I want only, so we want only constructive interference. Okay. So, if I have to fulfill this one, I have to fulfill this one. So, that is the reason I will get a certain modes like this, okay. And these modes that I get here, so if I write any general mth mode, that would mean that I will have m number of okay. So, there are certain number of oscillation before it goes to this 0 amplitude oscillation point, that is the 2 nodes. So, these type of nodes are known as longitudinal modes. These are along the axis, the propagation, wave propagation direction is along the axis, okay. So, these are known as longitudinal modes. Now, how many modes or which particular modes are within the spectral band of my particular active medium, that one can estimate, okay. and we will see that either toward the end of this class or in the following class, okay, and we would learn how to estimate those things. Now, we need to talk about another thing. So, when we say that I have longitudinal mode, okay, so mode depends on the combination of directions. So, longitudinal mode is along the axis of the laser cavity. So, immediately you can sense that there is possibly another type of mode, okay. Actually it is. Now, we have been describing this laser cavity by putting flat mirrors, okay. Now, the flat mirror has a drawback, okay. What is the drawback? That it cannot collect the off axis photons. So, the spontaneous emission which are little bit off axis, they can trigger the stimulated emission off axis also, and even if it is a slightly off axis, then they escape the cavity. So, the intensity of light in this particular case is not as great as it could be. Now, this problem can be arrested if we create the cavity, instead of using two flat parallel mirrors, we use two concave confocal mirrors, okay. So, we can use two confocal concave mirrors. To form the cavity. So, how will that look? So, they will look like this. So, confocal meaning that they will have conjugate focal lengths. So, their focal spot will be here for both of them. Now, if we consider the lights which are moving axially, axis still remain this, right? This is my axis. So, exactly like in this case, my photon will go back and forth, okay. So, I am not losing that characteristics. On the other hand, what do I have? What do I have extra is the following, that if suppose a photon is going in this direction, okay, suppose a photon is going in this direction, and in this system I will lose that photon. Here what will happen, because of its concave surface and because we have chosen it to be also confocal in this case, this will go here, okay. So, suppose this is coming from here, let me okay, adequate. So, so it will go here, and then again it will pass through the center, hit here, then it will become parallel to the axis, and then again it will follow. So, it will follow a route like this, okay. So, it is not getting lost. So, slightly off axis photons are also now a part of this amplification process, and you see every round trip is passing through the active medium, because my active medium will be at this focal point, right. So, I am not losing, and ultimately what is happening, so this is happening at this point also, this is happening at this point. So, ultimately when it comes out of the laser, I essentially have a beam like this, okay. So, depending on my mirror system, I will have, so this is my ultimate laser output. So, it will have its own beam width. So, there are several other things that the beam width depends on. Okay, we will talk about that. So, in such kind of cavity with confocal concave mirrors, since we are collecting the off axis photon also, advantage is that the intensity of the laser output is much more compared to this system. Now, because of its design, I will get some modes in the perpendicular plane, perpendicular to this axis. So, what I am saying essentially, suppose this is my whole laser, suppose I devise this laser, so everything is inside and all I am getting is an output, and suppose I expand this beam, okay, by a lens. What kind of lens I will use to diverge the beam? I will use a biconcave mirror, biconcave lens. So, this will expand the beam, right? This will diverge. So, essentially once it diverges, the beam diameter is very large at a distance, and if I put a photographic plate, so this is say my photographic plate, then I will see how the beam is physically distributed. Okay. So, what I can see? I can see some of these following stuffs. So, let me use a different color. So, in this photographic plate, I will see the distribution of the photon in the plane which is perpendicular to this axis. So, this axis is the axis of this laser beam, and I am just looking at a plane perpendicular to this axis, correct. So, what I can see in this photographic plate, I can see a homogeneous distribution of the beam across a central point. Okay. So, this beam is very nicely a circular spot. Okay. It can be something like this. So, it essentially has two lobes in this fashion. I can have like this, having 4 lobes, or I can have again 2 lobes is pattern, but these lobes are oriented in a different way. Now, what are these? These are called the transverse electromagnetic modes, okay, and they come with some subscript, let me call it PQ. So, this is, if I expand this one, this is called transverse electromagnetic magnetic mode. Okay. That was longitudinal mode, this is transverse mode, and you can see the longitudinal mode was along this axial direction. Here this is actually in the perpendicular plane to the axial direction. So, how do we get this TMPQ? I have showed the experimental design by which you can get it, and then how to read these things. Okay. So, essentially this PQ, these are the numbers of nodes in this plane, that is the perpendicular to the axis of the cavity, and in two perpendicular direction, because this is a plane, right. So, it can have this direction and it can have this direction. So, if I look into this direction, I will get what is the number of nodes, that is P. If I look into the other direction, I will get the number Q. So, here if I look in this direction, I see number of nodes 0. This is just a solid circle. So, there is no node. Okay. So, 0 node. So, TEM. Okay. So, first I am looking at this direction, I get or say okay, I started with this one, right. So, fine. So, in this direction I have no node, so I get a 0. In this direction the same, I get another 0. So, this is called TM00 mode. So, by looking at the beam profile, I will be able to tell which kind of transverse electromagnetic mode that the laser beam has. So, for example, if I look into this one, what mode this one has. So, this one again I come from this direction. So, I have no mode, right, because in this case there is no 0 intensity. Okay. So, if I look through essentially these, there is no 0, but here when I go, I have intensity and then there is a 0 mode, 0 point, point of 0 amplitude oscillation, and then again I have certain oscillation. So, this is essentially you have TEM. So, if okay, so let us make a convention so that we do not have any problem. So, first I will prefer, we will choose this direction as P and this one as Q. Okay. So, if I ask you in assignment or exam, you should follow this one. Okay. So, that we are on the same page, or at least one can mention which one is which one. So, in this case, if P is my first subscript, so here if I go, I have 1, and in this case I have 0. So, this is TM10 mode, alright. Now, what happens in this case, say this is, you can see this is just flipped on the other plane, other direction. So, this one will be TEM01. Now, this one you should be easily figuring out what is this mode. So, you can see this, if you cross this direction, there is one node. If you cross this direction, you have another node, correct. So, this is essentially TEM11 mode. So, you can keep constructing. Okay. So, knowing this preliminary few nodes, you can keep on constructing other types of nodes that are possible. Okay. In various cases there are applications of higher order modes, but most common is the TM00 mode. Okay. Most of the lasers that you will see will have TM00 mode. Certain cases you will have TM say 01 star, which looks like a donut. Okay. So, different types of modes will be there, but most common is this TM00 mode. I will share description of various different transverse modes with you. So, please go through them, and you will start understanding how to recognize which mode is which one, okay, how to name them, and it will be a good exercise for you as well. Okay. So, we have to now, with this knowledge that there are longitudinal and transverse modes, which we will use as we progress. Let us now again go back where we were discussing about certain practical concerns or issues involving construction of laser, where we talked about the concept of loss and gain. We mentioned that there must be a threshold beyond which you can get laser action, where your gain will exceed the loss. Okay. And we will now see that how to quantitatively estimate that threshold condition. Okay. All right. So, we need threshold condition. So, this is some condition beyond which we will see laser action, below that we will not see any laser action. All right. So, we have learned about population inversion earlier, and we also know that the rate of increase of intensity of the stimulated photons. So, what I am saying is that if I say intensity of photon is I, intensity of the stimulated photons is I, then rate of increase of this. So, when I say rate, that means there is a time component. This is proportional to the difference in the population of the excited and the ground state, so essentially, which is right. Now, if I go to somewhat equality, okay, I should be writing almost equal to into B, which is the Einstein coefficient, which is same for absorption as well as stimulated emission. So, I can use B21 equals to B12 equals to B, as we assumed in one of the previous classes. And we have this ultimately multiplied by this I. All right. So, this is actually identical to the equation that we have seen earlier. Okay, that is just the rate of a transition. Now, there we considered about the photon density and or the energy density, so either phi or rho. So, instead of that we are using this. Okay. So, but both of them are identical. So, at the end of the day we have seen this one. Now, in a practical sense, this states that we consider may be degenerate, may be non-degenerate. So, the general idea will be to take the degeneracy into account. Okay. So, if I have So, these are the two levels involved in the lasing action. So, this is level 2, this is level 1. You can have some other levels here and there, I do not care about that. Now, the degeneracy corresponds to this one if it is G1 and this is G2, then I can write this one as N2 minus G2 by G1 N1 right. So, okay, so we do not have any time left for this class. So, we will start from here in the following class and we will ultimately see what are the threshold conditions for lasing action. Thank you very much for your attention.